Hello, how y'all doing today? My name is Bernie Thompson, and today we're here to take a look at this 2009 Volkswagen CC. This CC has a drivability problem where the engine will barely run. So it's misfiring and running very poorly. So the first thing I want to do is put a scan tool on and see what DTCs are there so we can get a diagnostic direction. So let's go ahead and get the scan tool connected. We brought the data up on the scan tool and I can see that I have 11 DTCs. That's a lot of DTCs, guys. So the next thing I want to do is see what DTCs are present. Now the most important DTC that I can see right away is the crankshaft-camshaft correlation has a problem. Now we're also setting misfires on cylinder 1, 2, 3, and 4 along with various other codes. But since the shop has described that the car will barely run and I have a cam-crank correlation issue, I really want to start there. So the next thing we're going to do is we're going to get the scope and we want to get the signals from the cam and the crank, and we want to see if those are in time or not. So let's go ahead and get that scope set up. I've gone ahead and I've got the oscilloscope connected to the CC. I've got channel 1 connected to the crank position sensor. I've got channel 2 connected to the camshaft position sensor. I've got channel 3 connected to the ignition coil for number 1. I've got channel 4 connected to the GDI injector, and I'm using an amp clamp so it will be easy to see when the current flow is established for the injection period on number 1. And I've got channel 5 connected to the VCT solenoid. That's a solenoid that controls the high flow oil pressure to move the cam phaser. That way we can be able to be sure if that's contributing to our problem or it's working or it's not working. But whenever you do any kind of cam timing, you always want to be on the solenoids because that's what's moving the cam. And since we have a cam problem, we would definitely want that data. So now let's go ahead and start this engine up and gather the data so we can analyze it. We need to go ahead and set the oscilloscope up for the probes that we have on the engine. Since we put an amp clamp on 4, we want to go ahead and select the 20 amp setting, and we want to go ahead down here and we want to invert and 0. So this will give us the waveform correctly. Now what we are ready to do is get the data, so we're going to go ahead and start it. And now we're going to go crank the engine over and see if it starts and get the data whether it's cranking or running so we can try to make some determinations on what's wrong with this vehicle. Okay, now that we've gotten the data on the scope, we need to go ahead and look at what's here. So the crank sensor is turning quite a long time before we get a start. When this gets bigger, this is a VR, a variable reluctance sensor, and this is a magnet, and it's pulled across a winding. The faster it goes, the bigger the amplitude is. So this just tells me that the engine went faster or it actually started there. So I want to go ahead and I want to get the zoom. And we want to come into this front section right here. Now we want to go ahead and I want to separate these waveforms just a little bit so we can get a better idea. Okay, so the white is from the VCT solenoid, so I'm going to turn that off for just right now. Come back to that. Now, I can see look at how many revolutions I went. Multiple crank cycles before I got one event. This is the injector, and this is the coil. And once I got an injector and a coil, then we started. Now I already know that there's a problem because this should happen right away. So if we come over here and we blow this up, we can see where the crank started to go, and now I have one full revolution. I had a second full revolution, a third, a fourth, and in the fifth I finally could find the timing. Now, when you guys are looking at these starting, these should start within 1 to 2 full crank revolutions. I should have commands being put. So right away, I've got something problem with this command. We'll look at that here in a minute. But I want you to see how long it took to get the injector and to get the ignition coil to fire. The next thing is where these are firing. So let's go ahead and look at these across. I'm going to shut the crank off. We're going to come across and we're going to look at these. Now normally the injector fires when the intake opens, which is over here. This is in the exhaust plane and this is a GDI. I expect this to open 30 degrees after valve opening, which is closer to the tower. So this isn't happening in a time sequence. And here we've lost the injector totally. The injector has stopped firing here. So right away, the computer has some timing issues that we can see just by looking at several just basic waveforms, as we can see here. And we can see that the injector was firing closer to being right here. See how close we are to the green, and see how we're way away from the green right here? This is a fire cycle is from ignition to ignition. This is in a different position than this. That's changing because the computer must be confused on the inputs. So now is what I want to do is we want to go and we want to look at the inputs, so we need to go ahead and get the crank back up here. So here's the crank. I want to get my zoom window. And we want to come in. Now notice we have a narrow, narrow, wide, wide, narrow, narrow, wide, wide. Now, so this is my cam, and on this rising edge right here, it should be over here. So we're quite a ways away. So in order to determine how far off we are, we want to go ahead and we want to go out. We want to get some fire cycles over here where we got the ignition firing, and hopefully it's at least firing enough to be on time to where, for our purposes to get some data, it will be good enough. So I'm going to get the cursors and we're going to come in and we're going to mark the ignition, and we're going to mark the ignition. Now that's one fire cycle, and I can see that that is correct because I have my missing index from the crank to missing index. That's one crank revolution, that's two crank revolutions. So now we want to go ahead and we want to mark this. And now we've got this marked, so we're a fire cycle. So this is one complete fire cycle, and for this engine that's top dead center, bottom dead center, top dead center, bottom dead center, top dead center, or that would be my firing order. And we can all actually put that firing order in if we would want to. So now we can see 1, 3, 4, 2, our firing order. But what I'm more interested in right now is where we are in relation to this cam sensor. So we want to move this cam sensor up. So now I've got the cam sensor, and now I'm going to take the cursor and I'm going to move the cursor, and we want right about there, and we want to go ahead and we want to take this and we want to go on the second tooth rising. And roughly where this needs to be is on this rising tooth. So I want to get a little more clarity, so we're going to go ahead and zoom in. And now I want to get the cursor, and I want to move that cursor right about there. So from that edge right there should be falling where this cursor is to be in time. That gives me, I'm about 56 degrees out of time right now. So this cam is quite a bit out of time. And we know that it's out of time because it lost the injector. It totally starts going all over. First it's moving its timing position, and then it's just gone. So that would also be an indication that the inputs, the cam and crank, are having a problem, and the algorithm can't figure out how to control it, so it's lost. So this is this far out. Now the questions that we've got to ask right now is the crank off or is the cam off? We can't tell that by this data. So what I want to do is I want to go ahead and pull the number 1 ignition coil out in the spark plug, and we want to do an in-cylinder pressure reading so we can analyze the data. Once we can see the in-cylinder pressure, we'll know where the valves are actually opening and closing, and we can make a better determination on what's wrong with this engine. So let's go ahead and get that spark plug out. The ATS scopes support the pressure transducers from just being plugged in. This will give me a power ground and a signal generated out of the scope. It makes pressure transducer work really easy. We're going to use a pressure transducer that will read the exhaust pushes so we can match those to the cam timing. I've gone ahead and I've put a -30 pressure transducer into the port so we can get manifold vacuum. I've also terminated the coil, and this is a termination to ground. Whenever you're dealing with coils, always make sure that they're properly terminated so they don't arc and hit a pressure transducer or get an electronic component on the engine. Any spark that can jump to any of these components can definitely damage them. So now that we're connected, let's go ahead and set the scope up. We want to go ahead and set the scope up. The first thing we need is 25 inches of water. Channel 2 is on the ignition. Channel 3 is the 300-pound pressure transducer. Channel 4 is going to be the 30 inches. So we now have those settings. So we want to turn these off, and now we want to go ahead and zero those out. And now we're ready to go ahead and get the data. So let's start the scope and get this engine running so we can gather data. Now that we have the data, we want to analyze the data. The very first thing I want you to notice is we have 180 pounds at idle. So to have 180 pounds at idle, I want you to ask yourself, how can you have that much air in the cylinder to get the pressure? Remember, volume is equal to the pressure. If I have high volume, I have high pressure. So I had to increase the charge within the cylinder to have 180 pounds. In this case, I have a problem. It's indicative of a problem. I need to normally have 40 to 70 pounds at idle. I can go up to 100 pounds and that's okay, but when I start getting over 100 pounds, I gotta start asking myself, where did all the additional air come from? 180 pounds is way too much air. It's showing me I have a problem. Maybe to have that much air within the cylinder, I would have a hose or a plug out of the manifold, and I would have a large amount of air entering the manifold, bypassing the throttle plate, and that might do that. Another thing that could do this is the cam timing, and that's what we're looking at on this car anyway. If the two cam lobe center lines move and they come together, I'll have more overlap. If I have more overlap, the exhaust gases will come back into the cylinder and I'll have volume to compress. So I'm thinking that this has something to do with my cam timing right now. The next thing I want to do is I want to get my zoom window, and I want to come in here and we want to get a couple of these towers, and we want to blow these up to where we can see these better. So these are my towers. I want to go ahead and I want to get my cursors. And then we want to mark them. Now we have this as top dead center, bottom dead center, top dead center, bottom dead center, top dead center. This is the power stroke, the exhaust stroke, the induction stroke, and the compression stroke. So now that we have these, I can look and I can see the towers aren't leaning, they're pretty even, so that's a good thing. If they're leaning, it tells me I have a mechanical problem. At this point, they're not really leaning. I want to zoom in down here. Okay, right away, I see another problem. Do you see how the intake pull went below the red line? The red line is a 0, and the red is actually indicative of a command to fire the coil. But when the coil didn't fire, I have a 0 point coming through here. But do you see how I went positive? In other words, this waveform up here is more negative. I have negative pressure, and this is indicative of positive pressure. Now, if that's 0, when that piston is still coming up, I'm pushing pressure back into the intake. So what that indicates is the intake valve is opening much too early, and the piston is still coming up on top dead center when that intake valve opened, and I'm pushing the volume of the cylinder back into the intake manifold. That's why every one of these is going positive. That again is indicative that the intake cam is out of time. So we want to go ahead, and I want to zoom in a little bit more on this so we got some more definition. We'll remark the cam. So right here we can see this clearly how far down this is going now. So we've got a problem. Now I want to go ahead and I want to take my cursors So I want to go ahead and I want to get my cursors, and now I want to move this guy over here. And what I'm interested in is putting this right at the top dead center position, and then I want to measure over to where this fell. Now I can see that let's shut this off, I can see that that had a pull. I'm pulling vacuum, and then all of a sudden the valve opened and this goes down. Now if I look at the intake and I compare it with this, do you see how the intake came up and it's forced down also? Maybe even just a little earlier, maybe about there. So basically that's about where the valve opens, and I can follow that that happened at the exact same time in the cylinder. So that valve is opening this much, and we can see the difference is 50 degrees. So that intake opened 50 degrees early. Now that's close to what the cam timing said. Remember the two targets we saw, the crank and the cam? So the crank and the cam had an issue, and they were about 60 degrees, so 50, 60 degrees. We're seeing this repetitive. So that intake cam is opening way too early. Now the next thing I want you to look at is over here where we have this is the compression. Do you see how when the valve closed it's all the way down here, and this is at this marker right here? Well, if we take these markers and we go over here, so first off, that intake should come almost to 60 on this engine and close. So it's not. It's closing over here. So if I measure that difference, I'm 53 degrees. So basically this cam from this position to when it opened and this position to when it closed, both of them are saying that I'm about 53 degrees off. So the intake cam is definitely off. Now if I look at the exhaust cam, this is almost at top dead center, but this should be 30 to 60 over here. So this is a little off too. So in order to do this type of work, guys, what you always want to do is you need another place. I can't do just one. So these are pressure readings, and pressure can change. So I want to come over here and I want to get one more reading over here. And we want to do the same thing. So we're going to take our towers and we want to put the marker through the tower. We want to mark it, and now is what we want to do is we want to come back down here, so take our zoom window and we want to zoom in on this, and we want to see what's going on over here. And we can see that this pocket right here is occurring, right? So we'll take the cursor, Now we can see that that pocket in this, we're opening about 25 degrees. We really should be at 30, but since the pressure and we really don't have a lot of vacuum, this might be a little early when it's actually a little further over. The exhaust is closer to being timed correctly because that's within just several degrees. The intake is 50-55 degrees off. So the phaser on this engine is on the intake. So the exhaust is on its own and the phaser is on this intake. So what I'm interested in now is the phaser. Now, one of the things we didn't look at earlier, but I want to show you, we're going to go back out, and what I want to do here is I want to look at this phaser. Now this phaser, we can see that it's pulsing through the waveform, and I'm going to zoom in on this, and we can see that these got these little drops. Now this is quite common for a Volkswagen or an Audi to have these. So basically is what I want to do is we want to measure this, and we can see that we have 246 microseconds. Well, that's not enough on time to do anything to that solenoid. I can't turn the solenoid on with that kind of on time. These are its normal off position. So you'll see these type of waveforms when you guys get these cars, and they'll have this type of a pulsing waveform. But to actually get this to change, the duty cycle needs to come on longer. So this is in an off position, which is very normal. Once I set a code for the cam crank correlation, manufacturers don't go ahead and control the system anymore. They stop controlling it because they're worried that if the cams were off and they applied them, they could bend a valve. It's one of the possibilities. So this is saying that the phaser is not in operation. I'm okay with that. But these phasers on the intakes, they can break. And when they break, there's a little valve. These are spool valve assemblies that control oil to a vane motor. These are vane motors, and the vane motor, if I put pressure on one side or another, I can drive the cam one way or another. Now, since the intake cam is off, and since this isn't pulsing, I'm thinking that this is my problem here. But I want to do one more test really quick before we get to that phaser. I want to unplug the coils, and I want to go ahead and crank the engine and get a cranking waveform, and I want to evaluate it. So let's go ahead and get those coils unplugged and crank this engine. Now that we've gotten the cranking data, let's go ahead and analyze it. I want to go ahead and get my zoom window, and we want to come in and we want to look at these waveforms right here. I want to turn this other waveforms off for right now. So this is my waveform, so we want to go ahead and we want to mark these. Then we want to get the zoom window. We want to come down here and we want to look at this. Now right here we can see where the exhaust valve opened. So what I can do here is we can get our cursors. So we're at 40 degrees before bottom dead center. That tells me that that exhaust cam is operating correctly. But do you see where the intake comes all the way down? It doesn't come flat. It rolls all the way down. So one thing we can do is we can go ahead and we can process this waveform, and that's just going to clean up a pressure waveform. We don't process cam and crank, but we want to do this. So do you see how this is cleaner now, and it comes all the way down to the bottom dead center mark? It didn't come across and go up. That valve did not close where it should. That valve should close over here between the 30 and 60. So this intake cam is off and the exhaust cam is on. Now that's sort of what I wanted to see. I wanted to see that that was what was happening. So it is. So now is what my belief is, that this phaser has the problem. That has moved the intake cam significantly. And if the intake cam moves, then it's going to have this problem. So what I want to do is I want to pop the phaser out and I want to look at it. When these come apart, the valve assembly, these are very complicated spool type valves, and they break and they come out and they allow full oil pressure to move the system. So let's go ahead and get that valve out and take a look at it. Okay, I got the solenoid off of the cover. The solenoid just bolts in, and as what happens is this solenoid pin moves. So this is a winding, and we have a magnetic field. And when we apply a magnetic field, it pushes this pin out. This pin pushes on that valve, so they sit like this in the engine. When you apply current to this, and you apply and you can control the depth of that rod and how far this is pushed in or out. Do you see how I'm pushing that valve in and out? When you look at the side of this, this is a spool valve assembly. And if you look at this, do you see how I can see those channels inside there moving? Well, when this moves, I can move the position to where I totally block the oil flow off, where it won't return or apply, and I lock the phaser in a position. When I move it to another position, I put oil on one side of the vane motor. When I move it to the other, I put it on the other side, and then I can lock it. This valve is moving in here, and you can see these guys moving inside that channel, and that's directing my high pressure oil flow to the vane motor so I can phase that camshaft. Now what happens is this valve breaks, and when it comes out, I have full oil flow going to the phaser, and it holds it out. If we want to look at this right here, we can see that this one in this engine is broken. Do you see how this piston is sticking out? Do you see how high it's sticking out? Now look at the difference. Do you see how this one is in and this one is sticking out? This is broken. And what needs to happen now is this solenoid, this valve assembly, needs to be replaced. So we'll pull this one out and we'll get that one in, and then this vehicle will be ready to return to the customer. It'll fix the car's problem. Now what I want you to realize is the way I went about finding the problem. I checked the codes. The codes drove me to check the cam timing. I checked the cam timing with an oscilloscope. So we check the cam and the crank correlation, and the cam and crank correlation were incorrect. Also, the injector waveform was failing. It's going away. That tells me I have a problem. What that tells me is that the camshaft is out. The crankshaft sets ignition timing in the program. The camshaft sets the induction system up so it knows what stroke it's on. Now the computer will know when to inject the fuel. But when it's not sure where the injection point is on a GDI, it'll just shut the injector off. Again, that shows me that I have a cam problem. Then we looked at it and we could see that the compression waveform, the in-cylinder waveform, is out of time, and we also could see that the induction waveform was out of time. The induction waveform was opening way too early, and we could see that the cam, the intake cam, was out of time. Now that shows us that the exhaust was in time, the intake is out, and the intake is picked up by the sensor, and this is the control of the cam's movement. So then we have a good idea that this is broken. So once we get this in, the car's fixed. Be aware of how I went around doing this. I went about it by an event-driven diagnostic procedure where one test drove the next test until we came to the conclusion and found the problem. If you use this type of troubleshooting, you too will be successful in your service space.